Hi, my name is Rajiv Kumar. I'm a research scholar from the Department of Computer Science and Engineering, IIT Bombay. Today I will present the paper Data Efficient GAN or DEff-GAN for diverse attribute transfer for few-shot image synthesis. The paper is co-authored by Professor G. Shivakumar. Single image GANs are generative models that are modeled using a single image rather than using a dataset of images. InGAN and SynGAN belong to single image GANs that can generate samples of new configurations with combinations of patches from the training image. ConSynGAN builds on the same idea and further improves the training speeds over SynGAN. In general, these methods are optimized to maintain the internal patch statistics. If we consider applications like editing and harmonization, new patches can be cropped or pasted and the model can be fine-tuned such that the resulting model generates samples with the new patches adapted to the training image style. In this context, can we model patches from multiple images as pre-training free few-shot image synthesis method that enables diverse sample synthesis. In few-shot image synthesis, we mainly focus on single-class few-shot image synthesis that models the images of the same class and multi-class one-shot image synthesis that models the images from different yet related classes. However, we make a few assumptions for the same. There should exist similarities in image layout or content, and the objects and classes should be roughly aligned. In few-shot single-class image synthesis, we consider two or more images belonging to the same class to generate samples with visual attributes from multiple classes. For example, face images of the same person. In multi-class one-shot image synthesis, we consider one image each from k-related classes to generate samples with attributes of the related classes using a single image of each class. For example, flower images, face images from different people, cat and dog faces, etc. In short, can we perform attribute transfer between two or more images or classes for the above task in a unified framework? For the base case of few-shot image synthesis from two images, ConSynGAN was modified such that a different input image is selected in each iteration. However, the generated samples were affected by mode collapse and were incoherent. With face-centered images and those images with salient objects, this may lead to unrealistic samples. So what prevents single image GAN from modeling multiple images within the same model? To this end, we propose changes to overcome these issues and generate coherent samples. Here I briefly describe the methodology and the model architecture. We employ a progressively grown GAN based on ConSynGAN and hence share many commonalities with ConSynGAN. The network has a limited receptive field which is smaller than the entire image. We exploit this small receptive field to extend single image GAN for achieving few-shot image synthesis. The main changes are in the discriminator architecture with an auxiliary classifier branch and the objective functions and in the implementation. The multi-scale architecture with n scales capture the statistics of the image at different scales and allows control over the amount of variability between the samples. Training starts from stage 0 where a scaled image is synthesized using randomly sampled noise at the coarsest scale. The discriminator at each scale has the same receptive fields as that of the generator at that scale. After each stage is trained, Next stage, comprising of a few convolutional layers, is concatenated, resulting in a growing generator. While the existing architecture is sufficient for generating samples for the base case of two input images, this may not be effective when the number of input images increase. Mode collapse may manifest at the patch level as the absence of certain image regions or patches in all the generated samples. To minimize patch level mode collapse and improve the quality, firstly, the training batch size should include every input image. Secondly, we augment the discriminator to have a classifier branch in order to classify the image patches. With the limited receptive fields, this keeps the global structures intact while varying between patches from multiple images. We define the objective functions for the generator and the discriminator as follows. Equation 1 corresponds to the L2 reconstruction laws enforced between real images and the samples generated from fixed noise maps. Equation 2 corresponds to the GAN objective, which consists of adversarial laws between the generator and the discriminator and the reconstruction laws. The Markovian discriminator classifies each of the overlapping patches of the input as real or fake, and the auxiliary classifier branch classifies each of the overlapping patches into respective classes. We use DEff-GAN GP laws, which increases the training stability, and the final discrimination score is the average over the patch discrimination map. For the discriminator, the objective function constitutes of a source loss and a classifier loss. The source loss tells whether a sample is real or generated, as given in equation 3. For computing the adversarial loss, the input images are given to the discriminator with real labels, while the generated images are given as fake images. The classifier loss tells which class the sample belongs to, as given in equation 4. However, the class labels are available only for the real images. For a batch of randomly sampled noise from a normal distribution, we expect the generated samples to have attributes from multiple images. To enforce the same, the classifier loss for the generated images is minimized as the cross entropy between the classifier outputs and the labels of all input classes in a random fashion for the entire batch. For any random sample to belong to any random class, the generated sample includes the patches or attributes from multiple images and classes. Here, we visualize the results of few shot image synthesis on two input of female face images. The leftmost column corresponds to the real images, while the rest of the images are generated once. Here, we visualize the results of multi-class image synthesis on Pokemon classes with two images. The leftmost column has the real images, while the rest of the images are generated once. Here we visualize the results of one-shot multi-class image synthesis on two related classes of cat and dog. The leftmost two columns correspond to the real images, while the rest of the images are generated once. Here we visualize the results of multi-class image synthesis on Pokemon classes for 4 images. The leftmost column has the real images, while the rest of the images are generated images. We visualize the results of few-shot image synthesis on 5 inputs of related flower classes. The top row corresponds to the real images, while the rest of the images are generated once. Here we visualize the results of multi-class image synthesis on Pokemon classes for 4 images. The top row has the real images, while the rest of the images are generated once. Here we visualize the results of few-shot image synthesis on 10 inputs of Obama face images. The top two rows correspond to the real images, while the rest of the images are generated once. There exist different methods that can generate excellent results in a few-shot scenario. However, many of these methods are either pre-trained on large datasets or severely overfit in the range of tens of images. Even after overfitting, the samples have FID values in the range of 50, where the generated samples are mere reconstructions of the input images. Due to this, it is difficult to conduct a fair comparison of our method to existing few-shot image synthesis method. Therefore, we have limited the comparison of our method to MixDL only. MixDL is a pre-training free few-shot image synthesis method with minimal overfitting and mode collapse that focuses on mix-up based regularization on the feature space of both generator and discriminator. However, it is not as lightweight as our method. As we have already seen, constant GAN succumbs to mode collapse without non-trivial changes. The evaluation metrics used for the quantitative comparison are LPIPS, FID, and CFID. We computed the LPIPS metric for all generated images between consecutive image pairs for sets of 5 images and 2 images and compared the same in table 1 for MixDL in columns 2 to 5 and for our method in columns 6 to 11. Similarly, the LPIPS metric was computed between each input image and generated images for the set of 5 images and 2 images and compared in table 1 for MixDL in columns 2 to 5 and for our method in columns 6 to 9. The reason for lower metric values in some tasks is due to training limited to only 6 stages and lower iterations. Table 2 suggests that all generated samples share some attribute with each input image. Except for the case of 5 flower images, our method results in better LPIPS values than MixDL in the above table. DEff-GAN generates samples of excellent quality when trained on larger number of stages, which ranges from 8 to 10, and longer training schedules per stage, ranging from 8 to 12 iterations. We computed the FID metric for all generated images for sets of 5 inputs and 2 inputs and compared the same in table 3 for MixDL in columns 2 to 4 and for our method in columns 5 to 10. Except for the case of 5 flower images, our method results in better FID values than MixDL. CFID is a paired measure that operates on a paired real image and a generated image, matching the patch distribution between the images. We computed the CFID metric for all generated images for sets of 2 inputs and 3 inputs and compared the same in table 4. The CFID values were very large for our baseline and hence was avoided in the comparison. Also, the CFID values in table 4 imply that each generated sample from our method shared attributes with the input that was considered. When the input images are visually very different, there may be abrupt and non-smooth changes, leading to non-seamless texture blending and patch composition. When we generate with smaller number of scales or stages, the effective receptive fields at the coarser scale is smaller, allowing the model to capture only finer textures. The solution to this is to increase the number of scales where the structures of larger support emerge and the global object arrangement would be better preserved. As a result, high-resolution images require more stages and longer training schedules. In comparison to other methods that use datasets of images, the training time of our method linearly increases with the increase in the number of input images. We modeled a pre-training free lightweight GAN for performing few-shot image synthesis for single-class few-shot image synthesis and multi-class one-shot image synthesis. Our model preserves global structure of objects while adjusting the appearance and texture. And the fine texture and high frequency information matching the original image are realistically generated, resulting in diverse attribute transfer in a few shot scenario. Having more commonalities between images leads to large attribute transfer and helps to generate patches from all images rather than from a single image. The generated samples depict realistic new samples and configurations while preserving the visual content of training images. The code and sample inputs used in the paper and presentation will be made available on GitHub.